Okay, we are going to discuss about state space models. Okay, so what is the state space models and why do we need this? Before going to this, what is a transfer function? Transfer function is nothing but output by input. Okay, output divided by input. Now in the S domain, fine. Now we use this for different we actually learned how to find the transfer function for different systems, but what we have done so far is only for um, single input single output. Okay, so this is the system, this is the input, this is output. So we have done only for single input single output, that is SISO, single input single output. Okay, but what about multiple input multiple output systems? Okay, so many systems will have multiple inputs and multiple outputs. So for that kind of systems, we cannot use this transfer function. Even if we use this transfer function, suppose if it has say 3 inputs and 3 outputs, then how many transfer functions you need to use? You need to use 3 transfer functions you need to use. Okay, so that will become a little complex. Okay, so instead of one transfer function, if you use 3 transfer functions, the system will become complex. Hence we will not use that approach. Okay, so transfer functions is best suited for single input single output systems, but when you have the multi input and multi output system, so the state space models would be better. Okay, also another use of the state space models are, if you see the control, if you see the control system designer, just let's wait for it to open. Okay, by the time it opens, so the advantage of this state space models is that this transfer function was being used for PID controllers. Okay, it was used for PID controllers, but state space models are mainly used for um, different other control systems. Like this is a controller. PID is a type of controller. Similar to that, there are other control systems which you can see here. If you go to this, there are systems like model predictive control. There are controllers called as model predictive. So in such cases, the state space model is preferred compared to the transfer function model. Okay, so just wanted to show you, it's taking a lot of time to open that. Okay, fine. So especially this multiple input multiple output systems, and if you don't want to use a PID controller, if you want to use some other controller like model predictive controllers or some other type of controllers instead of this PID controller. PID is a basic type of controller. Okay, PID is a basic type of controller. There are many other controllers available which you can use. So if you see the tuning methods, You have this other methods like LQG design, loop shaping, model control tuning. Okay, so there are many other methods which does not use the transfer function model, but they use the state space model. Okay, so they use the state space model, but this PID tuning is fine with the transfer function model. So that's the state space model is basically in the form of matrix. Okay, transfer function had this numerator and denominator. The state space model is in the form of matrix. Okay, suppose for example, if we consider a spring mass system, so this is a mass, x is the displacement, k is a spring constant. What is the equation of motion for this?
mx double dot plus kx equal to 0.
Mx double dot plus kx equal to 0. So mx double dot is equal to minus kx, or x double dot is equal to minus k by m into x. Okay, so what are the variables that you need to know to completely understand the system?
Stiffness of the spring, mass.
Stiffness is not variable. Say k and m are the constants. Okay, k is say fixed, mass is fixed. Okay, now what are the things that you need to know to completely define this system?
The force acting on the mass.
Okay, you have also a force acting. Okay, um, but how do you, what is the output?
Displacement, sir.
Displacement. Okay, the position, I'll say position. Okay,
Yes, sir.
then if you know the position, can you completely define the system? Do you know everything about the system?
Um,
Or do you need to know anything else?
no, sir. For the system, position will do.
What about velocity?
If we differentiate it once, we'll get velocity.
Yeah, suppose if there is an initial velocity to this. Okay, if there is an initially itself, if it is moving, then you need to know velocity.
Yes, sir.
Okay, imagine if it's not starting from equilibrium position, you are already already assume that there is some initial velocity, the mass is moving. Okay, so you need to know the velocity and position. Okay, but do you need to know the acceleration?
We can differentiate velocity to get acceleration, sir.
So you can get from this, right? If you know the position,
Yes, sir.
you can find the acceleration. So position and velocity is sufficient to know. Okay, position and velocity is sufficient to know. Now what we do is um, so we write that equation mx double dot plus kx. I'll also take a damper. Okay, cx dot is equal to u of t. Now still I need to know only the position and velocity, right? Do I need to know anything else? Even
No, sir.
if I damper, If I use this damper, do I still need to know anything else other than this?
No, sir.
Mx double dot plus kx is equal to u of t also had position and velocity as the variables. Okay.
Yes, sir.
And this also has position and velocity as variables. Why? Because this also has velocity only, which comes from this. Okay, so
Yes.
this doesn't change the number of um, things that you need to know to define the system. Okay, these are called as state variables. State variables. Okay, state variables is to whether you use a damper or not. Okay, to completely define this. So that's the important point you need to understand from this. Okay, now what I'll do is I'll take the position x of t, okay, is equal to x1. Okay, I'll just write x of t equal to x1, whereas x dot of t is equal to x2. Okay, x dot of t is equal to x2. So which is also equal to what in terms of x1?
X1 dot.
X1 dot. Okay, now u of t is what? The input force. Okay, u of t is the force. I'll write it as u1. Okay, this is, I'll tell you why we are doing this. Now if I write it this way, if it will be u of t minus kx minus cx dot is equal to mx double dot. Okay, this equation is written like this. Now I use these things to write this. Okay, u of t can be written as u1 minus k x1 minus c x2 is equal to m. What is x double dot?
X2 dot, sir.
X double dot of t, x double dot of t is equal to x2 dot. Okay, mx2 dot. Now what you see here is, here it was double dot, here it is single dot. Okay, so what we have done is reduce the order. Okay, so here it was second order, here it is first order. So what we have done is we are writing the differential equation into two equations, which is of single order. Okay, so instead of two orders. So what is so this is equal to m into x2 dot. So what will be x2 dot equal to? It will be equal to 1 by m into u1 minus k by m x1 minus c by m x2. Okay, so just divide by m in this. Now what is x1 dot equal to? X1 dot is equal to x2. Okay,
X2.
so now here u is there, x1 is there, x2 is there. So in the same form, if I have to write, I can write it as 0 times x1, okay, plus 1 time x2 plus 0 time u1. Okay, so this is what it is. Now if I write that same thing x2 dot in this order, it will be minus k by m x1 minus c by m x2 plus 1 by m u1. Okay, so just written in this form, that's all. So you have these two, x1 dot and x2 dot. Now I'll just put it in a matrix form. I'll tell you why we are doing all these. Okay, so what I want to write is of this form: x dot is equal to ax plus bu. I want to write in this form the equation which we wrote. Okay, now instead of x dot I have x1 dot and x2 dot. Okay, so that is a matrix. X dot is a vector, so x1 dot and x2 dot. Okay, this forms the x dot equal to, okay, what is a? It is a into x you have to write, so 0 and 1 minus k by m and minus c by m. Okay, so this is 0 1 minus k by m minus b by m multiplied by x1 x2 plus, what is b? It is 0 and 1 by m. Okay, so it is 0 and 1 by m multiplied by u1. Only u1 is there, so u1. So this we have written in this form. Now what is this actually? This matrix talks about the dynamics of the system. A matrix talks about the dynamics of the system. Okay, this thing talks about what is the input. Okay, what is the input force and how it is going to affect. Okay, this is about the dynamics of the system. This is about the input to the system. Okay, so it is written of this form: x dot is equal to ax plus bu. Now there is another equation you need to write, which is of the form y is equal to cx plus du. Okay, so y is nothing but the output. What is the output? It is the position, the displacement. Okay, x of t, which is equal to what? X of t is defined as what here? It is defined as x1. Okay, y is equal to x of t, which is equal to x1. So how do you write y is equal to cx plus du with this thing? Y is equal to, it is 1x1 plus 0x2 plus what will it be? 0 into u1. Okay, so if I have to write this, how will I write? Y is equal to, what is c? 1 and
0.
1 and 0. This side it will be x1 and x2. Okay, plus 0 times
u1.
Okay, so this is how you write this. Y is equal to cx plus du. Now what is this cx? How the system is going to affect the output. Okay, so this is the output, y is the output, y is equal to x of t. So how this C matrix is going to affect this output, that is what the C will tell you. What D tells us, D consists of the feedback terms. Okay, if you use a closed loop system, then there will be D terms here, and how that input of that is going to affect the output. Okay, feedback affects the output, right?
Yes, sir.
It's the output. So that information will be there in the D matrix. For now, it is 0. Okay, for now it is 0. So what you understand from these two equations is x dot is equal to x plus bu, y is equal to cx plus du is A is going to have the information about how the system is going to behave, okay, the dynamics of the system, and this is going to consist of the input to the system. This is going to consist of the Cx is going to consist of the how the system is going to affect the output, okay, and then this is going to tell how the feedback affects, how the feedback input is going to affect the output to the system. So uh, you had this transfer function numerator by denominator, okay, similar to that. These are the two equations in the matrix form we'll be using for the state space model. These are the general, this is a general form, x is equal to ax plus bu and y is equal to cx plus du. Now how did you arrive at this? Okay, how did you arrive at this? We arrived at by deciding the state variables. Okay, if you see here, it is only the position and the velocity that you are going to find out. You are not going to find out, you are not going to find out acceleration. Okay, so the state variables is the minimum number of variables that is required to completely define the system behavior. Okay, so if you know position and velocity, you can find out acceleration. But if you know only position, if there is any initial velocity, that will not be able, that you will not be able to find out. Okay, if the initial velocity wasn't there, then with only position you can calculate velocity and acceleration. Okay, but if you have a damper, then velocity is required. Okay, if you have a damper, then velocity is required. So position and velocity is must. You can leave out acceleration, as you can calculate acceleration later from this data. Okay, so this is the state space model, and the application of this we'll be discussing. You may not understand completely in the first class, but as we go on, it will be fine. Okay, so this is a little bit advanced topic, and it will take some time for you to understand this. Okay, so not a problem if you are not understood completely, but uh, some understanding you must have got with this position and velocity, what is a state variable, okay, and how to write it in the form of this, okay, of this example. This is the example we took. This is the example we took, the spring mass and the damper also here. Okay, we have considered damper. So this is C. So this is what we have considered, and we wrote the equations for that. What we did was we just took this. We need to have only one dot instead of two dots here. Okay, so that's the thing we need to do. That is, from a second order system, you make two first orders. Okay, so that is what it is. And this is that y is equal to x of t is equal to x1. This is the second equation, and the first equation was this one. Okay, this is the first equation, this is the second equation, and this is what you get. Now, okay, so what is the transfer function for that system? What we wrote now, transfer function. Before going to the state space model, By now you should be able to tell me what is the transfer function of that. What is the output?
X, sir.
What is the input?
U of t, sir.
Transfer function, so in S domain. Okay.
Yes, sir.
What is the equation? What is the equation? Don't know. Mx double dot plus Cx dot plus Kx is equal to U of t. This is what we wrote. Take the Laplace transform of this. Ms square x of s plus Cs x of s plus K x of s is equal to U of s. So x of s common. What do you get? Ms square plus Cs plus K is equal to U of s. So what is the transfer function?
1 by ms square plus cs
X
plus
of
k.
s by U of s is equal to 1 divided by
ms square plus
plus
cs
Cs
plus k.
plus K. So this thing is a very simple one. By now you must be able to tell me immediately. Okay. So suppose if m is equal to 3, c is equal to 2, k is equal to 1. What is the transfer function? 1 divided by 3s square
3s square plus 2s plus 1.
2s plus 1. Okay. Fine. Now let's calculate what is A matrix equal to. It is 0, 1. What is minus k by m? Minus
Minus 1 by 3.
minus b by m is minus
Minus 2 by 3.
by 3. Okay. Where is the B matrix? This is the B matrix. B is what? It is 0 and
1 by 2.
1 by 3.
1 by 3. 1 by 3, yes.
Okay. What is C matrix? C matrix is 1 and 0.
1 and 0.
D is 0.
0.
Okay. Now, what I'll do, I'll go to the MATLAB. I have 3 minutes to go. So quickly, we'll type something. So we are all CLC. Okay. Now A is what? 0, 1. The next row it is minus 1 by 3 minus 2 by 3. Okay. B is 0 and then 1 by 3. Right. C is B is equal to C is equal to. Are you able to see the MATLAB screen?
Yes, sir.
Okay. C is this. D is
0.
0. Okay. Now I define G is equal to state space. SS is state space. A comma B comma C comma D. Okay. We'll run this thing. Say space. So what you see here is we have got the same thing. Okay, this is what we gave. This is what we gave. Okay, so this is a state space definition of that. Now what I am interested is to get the transfer function from the state space. Okay, So how do I get that is I collect the numerator and the denominator. Num is numerator comma denominator is equal to state space to transfer function. Okay, I'm converting state space to transfer function. Okay, a comma b comma c comma d. Okay, now uh, g1 is equal to transfer function of, take the numerator and the denominator which you got. Okay, now run this. So this is the transfer function. Okay, what is the transfer function we got? 1 divided by
1 by 3s square
3s square plus 2s plus 1. Divide by 3. This is 1 by 3.
Yes, sir.
S square plus 2 by 3 s plus 1 by 3.
Yes, sir.
Okay. Now what is that you have got here? The other screen. It is 1 by 3.
Nothing, sir.
1 by 3. S square plus 2 by 3 s plus
1 by 3.
3. Okay, so what we have done is we have calculated the state space model for that problem. Okay, and said this is the state space model, A B C D are the matrix of that. Okay, and then we collected the numerator and denominator of that state space to transfer function conversion. Okay, we are converting the state space to transfer function. Just to check. Okay, so this is the state space model information. Now taking g1 is equal to transfer function of this numerator and the denominator. So that will give you the transfer function. So what we have done is we have found out the state space model, and we are checking, we are converting to transfer function just to see if we have done it correctly. Okay, so this is the transfer function which we know and that it is correct, and so our state space model is also correct. Okay, so if you have understood only 25% or 30% of what I've told, it's fine. We'll be doing some more problems on this, and we'll let you know, we'll teach you how the state space model is going to help further. Okay, so let's continue tomorrow. Okay, we'll stop here. Any questions?
No, sir.
Questions? Okay, fine, thank you, bye.